Hi everybody, this is Vijayalakshmi, lecturer in physics in BRR and GKR Chambers Degree College, Palakal. Students, regarding to our fourth semester, here we learned about heat. Here we learn thermodynamics and radiation physics in our fourth semester. So our title is thermodynamics and radiation physics. First we go for thermodynamics. Thermodynamics is a branch of physics which deals with the transformation of heat energy from one body to another body. Here this radiation and transformation of heat is learned in this semester. We already learned about this thermodynamics in our intermediate level, which is about isothermal process, adiabatic process, temperatures, pressures, volume changes, and Carnot's theorem and refrigerator concepts. Today we just recollect about isothermal process and adiabatic process. So here isothermal process, when a thermodynamical system undergoes a physical change in such a way that its temperature remains constant, then the change is known as isothermal change. It means in a thermodynamical process the temperature remains constant during the process, then the process is simply said to be isothermal change. In this process, exchange of heat takes place between the working substance and its surroundings. This is a slow process. So, this isothermal change takes place very slowly. Hence, it is said to be a slow process. Here, Boyle's law holds good. So, PV equal to RT. For we consider 1 mole ideal gas, Boyle's law holds good in isothermal change. So, the working substance undergoing isothermal change, we can explain it with the help of a indicator diagram as given below. Here as shown the PV indicator diagram. It means pressure and volume plot on a graph. For 1 mole ideal gas, the indicator diagram is taking pressure on y-axis and volume on y-axis. Let 1 gram mole of ideal gas expand isothermally as shown in figure. Let Pi and Vi be the initial pressure and volume respectively, and its final pressure and volume may be Pf and Vf as shown here. At the state B, during isothermal process, the pressure and volume change. Let P and V be the pressure and volume at any intermediate state C as shown in the diagram. We assume that the pressure remains constant for a small increase in volume dV. It means here the pressure and volume may changes as for the small increase in volume dV. The work done by the gas during isothermal expansion we considered as PdV, which is equal to the shaded area in the diagram. Here the net work done by the gas when it expands from volume Vi to Vf is given by, here we consider for small expansion of gas from initial state Pi to Vf and Pf. It can be explained as with the help of integration. So total work done W is nothing but integral Vi to Vf PdV. For isothermal process PV which is equal to RT, then we can consider as P equal to RT by V. Therefore, the work done W which is equal to integral Vi to Vf, we considered as initial volume is Vi and final volume is Vf, then Vi to Vf RT by V dV. So, W which is equal to RT integral Vi to Vf we considered as RT by V dV, which is nothing but here RT is constant, then we can put it in front of the integration. Then we can write W is equal to RT integral Vi to Vf dV by V. Then integrating dV by V, it means log V. So we can write it as W is equal to RT log V, Vi to Vf within the limits. Hence, by substituting the upper limit and lower limit, we can get W is equal to RT log Vf minus log Vi. So, we can write it as RT log Vf by Vi to the base E. If we can write it in the base 10, we can multiply it with a constant W which is equal to 2.3026 RT log Vf by Vi to the base 10. If the initial and final volumes are V1 and V2 respectively, and similarly P1 and P2 are the initial and final pressures. Then the work done is given by W, which is equal to 2.3026 RT log V2 by V1 to the base 10. So in isothermal process we can observe that here temperature remains constant. When a thermodynamical system here undergoing isothermal change, we can study it. Then we go for next adiabatic change. When your thermodynamical system undergoes a change in such a way that no exchange of heat takes place between the surroundings and the systems is known as said to be adiabatic change. During adiabatic change, there is no exchange of heat takes place between the system and the surroundings. Here, during this change or during this process, Boyle's law does not holds good. In isothermal process, Boyle's law holds good, but in adiabatic process, there is a Boyle's law not satisfied. Hence, we can say that Boyle's law does not holds good. Under this change, the pressure P and volume V of a gas are related by as expression PV power gamma equal to constant. In previous isothermal change, we can take it as Boyle's law holds good, PV is equal to RT constant. But here Boyle's law does not holds good in our adiabatic change. We can write it as PV power gamma, which is equal to constant, where gamma is the ratio of two specific heats. We already know about specific heats. The relation between the specific heats is nothing but gamma equal to Cp by Cv. So the work done in adiabatic change may be explained as this is also considered for 1 mole ideal gas. Let 1 gram mole of ideal gas expands adiabatically from an initial state A to final state B. Then we can plot graph for this adiabatic expansion as shown in the diagram, as indicator diagram. Take it as plot of pressure and volume, and pressure on y-axis and volume on y-axis, and here also the initial pressure and final pressure are Pi and Pf, and initial volume and final volumes are Vi and Vf. Then we can write it as here the pressure and volumes respectively as Pf and Vf and Pi and Vi as shown below. Here let P and V be the pressure and volume of some intermediate state C for a small change in the volume dV from C to D. Let the pressure remains constant. Here we considered it as in adiabatic process the pressure remains constant. The work done by the gas during small expansion from PdV, this is equal to the shaded area CD in below diagram. Hence the net work done by the gas during expansion from volume Vi to Vf as given by the total work done as W is equal to integral Vi to Vf PdV. In previous isothermal process also we can calculate the work done. Here also we can calculate the work done for adiabatic change as we take it as PV power gamma equal to constant. For simplicity we can write it as PV power gamma equal to K. Then we can write P equal to K by V power gamma. We substitute this P equal to K by V power gamma in work done W, which is equivalent to integral Vi to Vf K by V power gamma into dV. Then we integrating this equation, here K is constant, then we can write it before the integration K into integral Vi to Vf V power minus gamma dV. By integrating this V power minus gamma, we can get W, which is equal to K into V power minus gamma plus 1 by minus gamma plus 1 within the limits Vi to Vf. We write the constants before the brackets, then we can write K by 1 minus gamma, Vf power 1 minus gamma minus Vi power 1 minus gamma. Here 1 by 1 minus gamma, we put this K value inside the brackets, then K into Vf power 1 minus gamma minus K into Vi power 1 minus gamma. Here this K value we already considered as PV power gamma. Then we can write 1 by 1 minus gamma above equation as Pf Vf power gamma, Vf power 1 minus gamma minus Pi Vi power gamma, Vi power 1 minus gamma. Here cancelling some terms and with the remaining terms as work done W, which is equal to 1 by 1 minus gamma Pf Vf minus Pi Vi. when the gas is compressed, here in adiabatic change, the gas is compressed, the work done is given by W, which is equal to 1 by 1 minus gamma P of Vf minus Pi Vi, or we can write it as W, which is equal to 1 by gamma minus 1, we take it minus as Pi Vi minus Pf Vf. If the initial and final volumes are Vi and Vf, here we considered as V1 and V2, and similarly initial and final pressures as at A and B, as then under adiabatic consideration, here we can write the above equation as W, which is equal to 1 by gamma minus 1 P2 V2 minus P1 V1. If T1 and T2 or Ti or Tf corresponding to the temperatures of initial and final temperatures, we can also write which is work done W is equal to R by 1 minus gamma Tf minus Ti, that is equal to W, which is R by gamma minus 1 Ti minus Tf. Hence PV equal to RT, we can write the above equation. This is about isothermal process and adiabatic process. Now our topic is about a reversible process. A reversible process is one which is performed in such a way that all changes occurring in the direct process are exactly repeated in the opposite order in restoring the system and their surroundings to their initial state. It means in a reversible process, the system undergoing processes and it recomes to its original state. Then the process is said to be a reversible process. All changes occurring in direct process exactly repeated in the same manner and reaches its original state. It means it regains its original state, then the process is said to be reversible process. Here the condition for reversibility or reversible process are nothing but thermodynamic equilibrium should be satisfied. Here in reversible process conditions, the thermodynamic equilibrium must be satisfied and there should not be any dissipative forces like friction, resistance, viscosity and etc. Since it is impossible to satisfy these two conditions perfectly, since this is an ideal concept, it is used in theoretical conditions in thermodynamics. So according to this dissipative forces, friction and viscosity, here these satisfying conditions are ideal concepts in thermodynamical conditions. So examples for reversible process are very slow condensation or evaporation process. It means slow processes like condensation and evaporation process are reversible processes. An extremely slow extension or contraction of spring. So slow extension or contraction of spring is an example for reversible process, and also melting of ice is also a reversible process. So in reversible process, the system regains its original state and original position. After the final state, it reaches its original state. Then the process is simply said to be a reversible process. So here next, irreversible process. Any process which is not reversible exactly is an irreversible process. It means which process which is not exactly repeated, then the process is said to be simply a irreversible process. So in the universe, all natural processes are irreversible. Natural calamities, all the processes are which is examples for irreversible processes. So here some examples for irreversible process are heating by sending current is an irreversible process. It means sending current by heating is an irreversible process, and heat transfers between bodies at different temperatures. During different temperatures, heat transformation is also an irreversible process example, and sudden expansion or contraction of a spring, which is also an example for irreversible process, and rapid evaporation or rapid condensations are also irreversible processes. So in a reversible process, the process which is exactly repeated in the opposite sense and it regains its original state. But in irreversible process, the process which is not repeated exactly in the same manner and reaches its original state, then the process is an irreversible process. And these are the examples for reversible process and irreversible process. So let us discuss about an example for a reversible process, which is nothing but a Carnot heat engine, which is a ideal theoretical concept. This is an example for reversible process. Hence, Carnot's reversible engine is a reversible process example. So, a heat engine is a device to convert heat energy into mechanical work. Here, this Carnot heat engine was developed by a French scientist or French engineer, Sadi Carnot. Hence, this theory is said to be Carnot's reversible engine. So, in a heat engine, it is a device to convert heat energy into mechanical work. Here, the heat energy is completely converted into mechanical work. Hence, it consists of the following parts. But practically, it is not possible. But it is a ideal concept. Hence, it is a theoretical engine. Hence, Carnot heat engine is an ideal concept. Hence, it is said to be a theoretical engine. It has the following parts. The four following parts consist Carnot's heat engine. One is the working substance. Here, the first substance is said to be first part as the working substance, and second the source of heat, and third one the sink, and fourth one insulating stand. These are the four parts in Carnot heat engine. I repeat, the first part is the working substance, second one source of heat, third one the sink, and fourth one insulating stand. Now let us discuss about the stepwise for the parts in the Carnot heat engine. First, the working substance. The working substance is an ideal gas enclosed in a cylinder. Here we consider 1 mole ideal gas which is enclosed in a cylinder piston arrangement. Here we consider a cylinder piston arrangement. Here the cylinder is perfectly non-conducting walls but conducting base. It contains unmovable frictionless free piston which is contained for moving the ideal gas in the piston cylinder arrangement. So here the working substance is an ideal gas enclosed in a cylinder piston arrangement, a cylinder with a perfectly non-conducting walls and perfectly conducting base fitted with the frictionless non-conducting piston. This is the arrangement in the working substance for first part in Carnot heat engine. And the second part, the source of heat. A hottest body in the universe always, and it means a hot body of high thermal capability maintained at a high temperature T1K serves as a source. The high thermal capacity of the source is necessary so that on taking heat from it, no change of temperature occurs. It means we take some of the temperature from the source of heat, then the temperature of the hot source never change. It means always it is at a high thermal capacity T1 Kelvin temperature, then it is said to be source of heat. And next, third part is sink, a cold body maintained at a lower temperature. It means in the universe, regarding to this Carnot heat engine, it is always a coldest body. It means the sink. The sink is always a cold body maintained at a lower temperature 2K and serves as a sink. Usually this is a surrounding atmosphere. Here the surrounding atmosphere acts as a sink. And last and fourth, the insulating stand. To make the whole system perfectly non-conducting stand is put on the base of the cylinder. So here for maintaining the system in Carnot heat engine we are using an insulating stand. This insulating stand make the whole temperature of the system keeping as constant. Here the piston, cylinder, source, insulating stand and sink can be understood with the diagram as given below. Here this is the piston, frictionless free piston, and cylinder. Here the cylinder, the walls are made with non-conducting but the base is perfectly conducting, and 1 mole ideal gas is taken in the cylinder piston arrangement, and source T1 Kelvin temperature which is at the highest temperature which is said to be source, and sink T2 Kelvin temperature which is always the coldest body which surroundings acts as sink, and insulating stand to make the whole system maintaining. Here we are using an insulating stand. So here this Carnot heat engine can be explained with the help of Carnot cycle. Here the Carnot cycle consists of 4 parts. So the working substance is made to undergo a cyclic operation made of 4 parts like isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression. These are the 4 steps during this Carnot heat engine. What are they? Are isothermal expansion and adiabatic expansion, isothermal compression and adiabatic compression. By using these 4 steps, we can explain the working and efficiency of this Carnot heat engine. This can be explained with the help of an indicator diagram. We already discussed about this indicator diagram, PV diagram, in isothermal expansion, and it means isothermal process and adiabatic process. Here we are undergoing the ideal gas isothermally, adiabatically, expansions and compressions. Hence we make a plot of graph along PV graph, x direction P and y direction V. This diagram can be plotted as all these 4 operations are shown in the indicator diagram. Here isothermal expansion. Consider 1 gram mole of gas is contained in the cylinder. Let initial state of the gas is denoted by A. Here the initial state of the gas is indicated at A. Here the initial pressure is P1 and volume is V1. Then the gas expands isothermally. Here the gas expands isothermally. Here the beginning step at A, pressure is P1 and volume is V1 during the temperature T1. Consider that 1 gram mole of a gas is contained in the cylinder. Let initial state of the gas is denoted by A on indicator diagram, where it has the temperature T1 and pressure P1 and the volume V1. The cylinder is placed on the source. Here we can understand this Carnot heat engine with the help of these 2 diagrams, indicator diagram and this piston cylinder diagram. So we use these 2 diagrams, we can easily understand this. Here the cylinder piston arrangement, the initial state of the gas is denoted by A on indicator diagram, where it has the temperature T1 and pressure P1 and volume V1. The cylinder is placed on the source and the piston is moved slowly upwards so that the gas expands isothermally. Here the gas expands isothermally. In this operation, the pressure of the gas falls and volume increases. Pressure falls and the volume increases in this operation. Hence, it should be remembered that fall of temperature is compensated by supply of heat from the source. The final state of the gas is represented by B. Here the gas expands isothermally from A to B. Here the gas expands isothermally from A to B. Thus the isothermal expansion of a gas is represented by the curve AB on the indicator diagram. Let the quantity of heat absorbed from the source. In these steps, here the piston cylinder arrangement is placed on the source, which is always at higher temperature T1K. Then the quantity of heat absorbed from the source in this process be Q1. Here the heat engine extracts heat from the hot source, as take it as Q1. This is equal to the amount of work done, W1 by the gas in the expansion from the state P1 V1 to the state P2 V2. It means Q1, the work done, which is equivalent to quantity of heat absorbed by this isothermal expansion from A to B, as Q1 is equal to W1, which is equal to integral V1 to V2 PdV. Here the work done is nothing but quantity of heat extracted from the source. Hence, W1 is equal to integral V1 to V2 RT1 by V dV. We already discussed this isothermal process. Hence, we can write the quantity of heat Q1, which is equal to work done W1 is nothing but RT1 log V2 by V1 to the base E, which can be indicated with the help of in the indicator diagram graph as area of A, B, B dash, A dash, A. This can be treated as equation 1. Hence, the gas expands is isothermally from A to B. The work done we get as equation 1. Then the gas expansion adiabatically from B to C. Here the next step in the Carnot cycle is adiabatic expansion BC. The cylinder then detached from the source and is placed on insulating stand. Here the cylinder is detached from the source and is placed on the insulating stand. The piston is allowed to move further adiabatically till the temperature of the gas is same as that of the sink T2K. Hence the gas does external work at the temperature of internal energy. Here the gas utilizes the internal energy and doing this external work. Here we place the cylinder piston arrangement on sink. Hence, the expansion is shown by the curve BC. It means non-conducting. The energy, the expansion is shown by the curve BC. In the final state, the pressure and volume of the gas are from B position to C position as P3 and V3 respectively. The work done W2 by the gas is given by W2, which is equal to integral V2 to V3 PdV. Here the gas expands adiabatically. Hence, we can write the integrating terms and we get P power gamma, which is equal to K. We discussed in adiabatic process. Hence, P equal to K by V power gamma, which is equal to work done W2 integral V2 to V3 K by V power gamma dV. Nothing but integrating the above terms, we get V power minus gamma plus 1 by minus gamma plus 1 within the limits V2 to V3. By substituting the upper limit and lower limit, we simplifying, we have the work done W2, which is equivalent to R of T1 minus T2 by gamma minus 1. Here by simplifying this, we get area of B, C, C dash, B dash, B. This is the work done for gas expands adiabatically during the second part of the Carnot cycle. And next, after this stage, the pressure of the gas is much reduced and it has lost its capacity of doing work. Here in adiabatic expansion, the pressure of much to be reduced and it has lost its capacity of doing work. So the gas brought back to its initial state P1 V1 by the following isothermal compression and adiabatic compression. So the next step is isothermal compression CD. In this, the cylinder is separated from the insulating and placed on the sink at T2. The gas is compressed very slowly till the gas attains the state D, where pressure and volume are P4 and V4 respectively. Here, the heat of compression so developed must through the skill. So, the operation is shown by the curve CD. Let the quantity heat reached to sink be Q2. It means in Q1, the first step, isothermal expansion, quantity of heat extracted is Q1, but in isothermal compression CD, the quantity of heat rejected, which is nothing but Q2, it is equal to the work done by the gas. Hence, Q2, nothing but work done, W3, which is equal to integral V3 to V4 PdV. Here, P we know, according to Boyle's law, in isothermal expansion, we can write it as V3 to V2 RT2 by V dV. By simplifying this, we have the Q2, nothing but quantity of heat rejected, which is equivalent to work done W3 minus RT2 log V3 by V4 to the base E, area of C D D dash DC, which is considered as equation 3. And next, adiabatic compression dA. This is the final stage of the process and last stage of the Carnot heat engine adiabatic compression. In this process, the cylinder is detached from the sink and placed on the insulating stand. The gas is compressed such that it undergoing slow adiabatic compression till the state A is again reached. Now the temperatures from T2 kelvins to T1 kelvins, this change shown by the curve dA on the indicated diagram. The work done W4 on the gas during this process will be W4, which is nothing but integral V4 to V1 PdV minus R T1 to T2 R by gamma minus 1 area of D dash A dash AD. This is equation 4. From equations 2 and 4, we can conclude that work done W2, which is equal to work done W4, and hence the net work done nothing but W1 minus W3, quantity of heat absorbed by the gas Q1 minus Q2, which is equivalent to W1 minus W3. Here, by the 4 steps of Carnot heat engine, isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression, we can make it as the efficiency of the engine. Here, the efficiency of engine can be calculated in order to calculate the efficiency of heat engine, we should calculate the work done and the amount of heat taken. Let Q1 be the heat taken during the isothermal expansion at a temperature T1 and Q2 be the quantity of heat rejected at a temperature T2. So, during this, the efficiency is defined as eta, which is equivalent to work done by the engine, which is divided by heat taken from the source. It means heat converted into work, how much amount of heat is converted into work, and ratio heat taken from the source. It means eta, which is equivalent to W by Q1. It means work done is Q1 minus Q2 by Q1. It means Eta efficiency 1 minus Q2 by Q1, which is equation 5. The net work done by the gas, it means total work done by the gas is, which is nothing but W. Total work done by the heat engine is W1 plus W2 plus W3 plus W4. It means isothermal work done, isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression. These 4 steps, we can write the total work done as W, which is equal to RT1 log V2 by V1 to the base E plus R of T1 minus T2 by gamma minus 1 minus RT2 log V3 by V4 to the base E minus R of T1 minus T2 by gamma minus 1 RT1 log V2 by V1 minus RT2 log V3 by V4. This is the equation 6. Points B and C in the graph lie on the same adiabatic, hence we can write it as T1 V2 power gamma minus 1, which is equal to T2 V3 power gamma minus 1. Here by simplifying this, T1 by T2, which is equivalent to V3 by V2 whole power gamma minus 1. This is equation 7. Again, the points A and D lie on the same adiabatic, hence we can write it as T1 V1 power gamma minus 1, which is equal to T2 V4 power gamma minus 1. Then T1 by T2, which is equal to V4 by V1 whole power gamma minus 1. From equation 7 and 8, we can write V3 by V4, which is equal to V2 by V1, substituting this value in equation 6. So this is the simplification, and substituting the steps, we can write this work done R of T1 minus T2 log V2 by V1 to the base E. It means the efficiency eta equal to, we calculate the work done by quantity of heat extracted from the source ratio. Then we substitute these terms, eta which is equal to R T1 minus T2 log V2 by V1 to the base E divided by R T1 log V2 by V1 to the base E. It means eta which is equal to T1 minus T2 by T1, 1 minus T2 by T1. This is the efficiency for Carnot heat engine, and this is the complete